So in this video, I want to go over a couple things. First of all, what I see is the three major differences between the Bayesian versus the frequentist approach to statistics. And secondly, I want to review the vision of this seminar and what I hope you got from it. So the first difference between the Bayesian and frequentist approaches is that they have different interpretations of the meaning of the word probability. So the frequentist sees probability as long-run relative frequency of some event, whereas the Bayesians think of probability in terms of belief or uncertainty. Now what I want to do is look at the globe-tossing experiment. And so with the globe-tossing experiment, we said this thing. The probability that theta is equal to 0.5126 is equal to 0.0170, and this expression contains both the frequentist and the Bayesian view of probability. So we'll think first of the frequentist and the notion of probability as long-run relative frequency. So we see here this expression, theta is equal to 0.5126. What that means is that the probability of a randomly selected point on the Earth being water is 0.5126. How does this relate to long-run relative frequency? What it means is if we were to take our globe and toss it an infinite number of times, then the frequency of occurrences where we would land on water would be 0.5126. So that's the frequentist part of this expression. The Bayesians, what they do is they take this thing and say it's equal to that, and they're referring to belief. So, with grid approximation in our globe-tossing experiment, we had these 200 values, each one shown by a separate dot in our posterior. And what this expression means is that our belief, if one of these 200 points is the true proportion of the Earth covered by water, our belief that the actual proportion of the Earth covered by water is equal to 0.5126 is 0.0170, as opposed perhaps to our belief that the true proportion of the Earth covered by water would be 0.75, would be only 0.002. I want to explore this again just a little bit further to bring out the difference between frequentists and Bayesians. A frequentist might look at this plot and say that it's nonsense. You cannot assign a probability distribution to the proportion of the Earth covered by water because that thing is not a random variable. The proportion of the Earth covered by water is a fixed value, and it's equal to 0.71. So how can you assign a probability distribution to something that's fixed? And the reason that that happens is the Bayesians and frequentists have a different view about what we mean by probability. So from the Bayesian point of view, these probabilities here reflect our belief, whereas this 0.71 reflect the way the world really is. Let's do another example. Let's consider we've got a coin. We flip it. Initially, it's spinning in the air. It lands on the table. We cover it up by our hand. We remove our hand to discover that, in fact, it came up heads. So what's the probability of it being heads? And let's look at it from both the frequentist and the Bayesian perspectives. Regardless of whether one's a frequentist or a Bayesian, well, it's still in the air spinning. They're both agreed that there's a 50-50 probability that it's going to be a head. Once that the hand has been removed and we see that it's a head, we know for certainty that it is a head. The distinction occurs when the coin is on the table covered up by the hand. From the frequentist point of view, that thinks about the way the world really is, once that coin has landed, the issue has been settled. It's either it's either a tail with a probability of 0 of being a head, or it's a head with a probability of 1 being a head. That's the way the world really is. But the Bayesian, who focuses on belief, nothing has changed between when it was spinning in the air and when it was covered by the hand. At this point, the Bayesian still believes there's a 50% probability, based on their belief, that it could be a head, and you don't get to change from 0.5 to 1 until the hand is removed and the coin is revealed to be a head. A second big difference between frequentists and Bayesians is that in frequentist analysis, the outcomes are determined entirely by the data. With the Bayesians, the outcomes are determined by a blending of the data as well as the prior. So, a few points to make about that. First of all, this idea that we have some prior beliefs, we get some data, and then on the basis of data, we adjust our prior beliefs to arrive at posterior or updated beliefs. That just strikes me as a good way for rational people to approach the world. Second thing is, from the frequentist point of view, this choosing of a prior introduces subjectivity. The Bayesian might push back in a number of different ways. They would say that, yeah, but when you really think about the way we do frequentist analysis, that can be pretty subjective as well. They point out that if you're really not comfortable with assigning priors, you can assign equal probabilities to each one of the values of the parameter, produce a flat prior that allows the data to speak for themselves without any influence of the prior, and then informed priors allow us to leverage previous information in order to improve our analysis. Third point to be made is there's all sorts of packages available. We went over one, BRMS, that use fairly simple code to implement Bayesian data analysis. If you're going to use one of these packages, it really behooves one to figure out how those packages are assigning their priors. And then the third difference is the frequentists tend to look at the probability of the data conditional upon the parameters, whereas the Bayesians, the probability of the parameters conditional upon the data. The example we're going to do is the notion of the IQ of IB students. So the data is going to consisted of y bar equals 111 based on n is equal to 9, and instead of this general theta, use the symbol mu here, not there, the word mu here, and these things are exactly the same. So I want to do this comparison between frequentist and Bayesian two different ways. First way, think about the comparison between a p-value of the frequentist and posterior distribution of the Bayesian. Not totally a fair comparison between frequentism and Bayesian per se, but rather just a comparison of this one thing, the p-value with the posterior distribution, and then go on to compare the confidence interval of the frequentist with the credible interval of the Bayesian, which is kind of a good, legitimate head-to-head comparison because they're both doing the same thing, but they're both trying to create an interval. So let's begin first with this comparison of the frequentist p-value and the Bayesian posterior. And they're both going to start off with the idea that they got the research funded based on a research hypothesis that the IQ of the IB students was greater than 100. So what the frequentist does is that they begin by positing a null hypothesis that contradicts the research hypothesis. So their null hypothesis is going to be null hypothesis is that mu is equal to 100, and then they calculate the probability of observing the data, which again was y bar equals 111 on n is equal to 9 samples. And when they do that, what they get is this. So here's the null hypothesis. U is equal to 100. And what's the probability of getting a mean of 111 or more based on a sample size of 9? There it is right there. There's 111 or more. This probability is 0.0139. So this is a very small number. It suggests that this thing here is implausible. So the data contradict the null hypothesis. The null hypothesis contradicts the research hypothesis. So because this double negative, this small value here is viewed as evidence for the research hypothesis. In contrast, the Bayesian approach is far more direct. We could use that derived function if we wanted to, that derived function prob. We saw that we could come up with this 0.0139, but more importantly, it can give us directly what we really ought to want. We're interested in the mean IQ of the IB students. There we see it right there. for every possible value of the mean IQ of the IB students, mu, we've got the probability that it in fact is the true value. Now move on to confidence interval versus credible interval. We can set these things up so we get exactly the same value in both cases, but the interpretation is quite different. The whole idea about confidence interval is that confidence intervals really arise as a process that yields intervals that are going to straddle the fixed mean 95% of the time. So we do in our experiment and we create this particular confidence interval. But if it's a confidence interval, we've just got this value. We don't know whether this particular value straddles the true mean or it does not. All we know for certain is that it was obtained by a process that's going to give us intervals that straddle the true mean 95% of the time. But then what we go on to say is, okay, either one of two things has happened. Either this thing does in fact straddle the true mean, or a rare event has occurred. And basically we're deciding that, very likely that a rare event hasn't occurred, and therefore we give ourselves permission to think that this interval, which is a random variable, straddles the true mean, which is fixed. In contrast, the Bayesian is far more intuitive. I mean, most people, if you said that hey, I calculated a confidence interval that went between those two numbers, most people are probably going to intuitively think not of this, but rather of this, that 95% probability that the true mean lies between these two values. So the Bayesian approach clearly has the advantage of being more direct and intuitive. But again, we got to give the frequentists their due in that this is, again, merely a statement of belief, whereas this provides a perhaps better long-run error control because it relates to the way the world actually is and is not merely belief. So to finish off, what I want to do is I want to think about the vision that I had for this seminar. I want to think of it in terms of three groups of participants. And the first group will be those who will be read or reviewing publications using Bayesian methods. Given how powerful Bayesian statistics is, given that its importance is increasing, this pretty much includes everyone. My hope is that as a consequence of participating in this seminar, folks will get more information, get more knowledge when they read papers that use these methods. And I'm hoping that increase in information and knowledge will be adequate to justify the effort that was put into this seminar. And the second group will be those who use our packages. And we went over one in particular detail, BRMS. There's a bunch of others. They're shown here. And all these packages run Bayesian analysis in the background. They're tempting. Why? Because they involve fairly simple code, and they're very powerful, but they are, to my way of thinking, dangerous, because unless one is very mindful about what one is doing, then it's very possible to obtain output that is plausible yet completely erroneous. And so what I'm hoping is that as a consequence of participating in the seminar, anyone who uses these packages is going to have enough understanding of Bayesian methods to use them appropriately. And then there's the final smaller group. The smallest group are those that might eventually write code directly to implement Bayesian analysis in something like runjags or winbugs. And the way that I think of that is that, writing code in winbugs is equivalent to kind of scaling Mount Everest. And if that's the case, then this seminar gets one to base camp. So in other words, the seminar provides the foundation, but the biggest challenges lie ahead. So, in summary, I hope you found this seminar interesting. I hope you found it useful. I wish you the best for the future. Cheers.